Good morning. I'd like to welcome you to the EMC Live webinar, Power and I/O Line Testing Standard Updates for Military and Aerospace, CE, Energy Matter Industries. My name is Helen Flood, and I'll be administering this webinar today. I'm the project manager at Interference Technology, the host and creator of this event. EMC Live is a new and innovative 3-day online event hosted by Interference Technology. The event highlights practical information and topics and will include roundtables, webinars, and videos on everything EMC related. Best of all, there's no charge to attend. Please visit the event website at www.emclive2014.com and plan on joining us for any of the remaining sessions today. This webinar is presented by Jason Smith. Jason is the EMC Sales and Marketing Manager for HP Technologies. Jason graduated with a BS from University of Delaware in 1997, majoring in engineering technology. He has over 17 years experience in the EMC industry. He joined HP Technologies in January 2012. In his current position as EMC Sales and Marketing Manager, Jason covers EMC marketing in North America for their partner products. This webinar is sponsored by HP Technologies, a company focused on providing its clients with top quality, fully compliant EMC test instruments. Its staff has been supporting the EMC testing community by designing, producing, and distributing the best in EMC test instruments for over 2 decades. HP Technologies covers all aspects of EMC testing for immunity and emissions. The highest level of support is HP Technologies' main focus and part of every product. A recording of this webinar and downloadable PDFs will be available on our website next week. Our webinar today will be interactive. We encourage you to ask questions at any time during the session. Take a look at your GoToWebinar navigation pane. This is the box you see in the corner of your screen. If at any time you have a question, we ask you to use the type box and hit send. To minimize or maximize the screen, click the arrow button. To raise your hand to ask a question or report an issue, click on the hand icon. We will present this topic for 35 minutes, followed by a 10-minute question and answer session. At this time, I would like to hand over the webinar to Jason, who will begin the presentation.
Well, thank you everybody for joining. I have to tell you, this is my first webinar, so not seeing everybody is kind of a little strange for me. So in my background, I do have 17 years in the EMC industry, 7 years as a lab manager for independent EMC tests. And the commercial, for the commercial and military test markets. I've also worked 8 years as an application engineer for EMC and RF and a technical lead for a company, and of course 10 years now at HP Technologies. Now I've been on participating member of many IEC and EMC committees. So today we're going to go over some of the recent updates in the EMC standards for the IEC 4-3 standard for harmonic emissions, the 4-4 for EFT and burst, 4-5 for surge, and a new standard 4-19 differential mode testing. And we'll go over MIL standard 461 and the new G proposed changes. This year, 3 standards have been updated and 1 new one. The 3-2 for harmonics emissions, 4-5 for surge, and 4-19 is a new standard, all released earlier in 2014. For the IEC 61000 3-2, it supersedes in the previous version, so we're at edition 4 now. There was a clarification of the standard for repeatability and reproducibility of the measurements. This really shouldn't have too much of an impact on your test equipment. If you met the edition 3 requirements, you should meet through edition 4. Where the major change of the standard came was a lot of clarifications in test methods. So this standard has a lot of unique or specialized requirements for the different IT equipment or audio amplifiers and such, and it redefined or defined a lot of those test methods more clearly on how equipment is set up and tested too. But as far as test equipment goes, it really shouldn't be too much of a change. 4-4 wasn't released this year. It was released in 2012, but it's pretty recent. It's still new and fresh in many people's minds, so we'll go over all the changes that happened with the 4-4. And also in this presentation, I do have actually a lot of slides here. We're going to glance over some of them pretty quickly, but I thought the information there would be important for later looking at if you download the presentation. But in 4-4, there was the figures were moved into the text, whereas before they were at the end of the standard. They added a mathematical formula for the pulse, defined a characteristic for the test load impedance, CDN calibration. The tolerances have been enlarged from the previous standard. Calibration of the coupling clamp with a transducer plate, so there's some new equipment required there. And there's a new test setups. And of course, measurement uncertainty has been added, as it has been for many of the standards. This is the mathematical formula. I'm not really going to go too much into that. And it's the wave shape from the formula. So the test load impedance has been changed or defined for up to 400 megahertz. In the old edition 2, there was no real frequency requirement for the test load. So you have a 50 ohm and a 1K ohm test load, and both of them have to have a tolerance measured up to 400 megahertz. So here's an example of a 50 ohm test load measurement. As you see, up to 100 megahertz, it's pretty flat, and up to 400 megahertz, it's still 1.5 dB tolerance, which is well below the 3 dB requirement. Calibration of the CDN, which was a requirement in the old standard, which required a common mode coupling to all lines, and then a measurement of each individual line. So the waveform shall be verified at the common mode output of the CDN with a single 50 ohm termination. The verification performed the generator output at 4 kV. Of course, with the 50 ohm load, it produces a 2 kV output. The functionality verification of each single CDN path is recommended. Now it's required. So we have to test each path. The rise time of the pulse, 10 to 90% rise time, has a new tolerance of plus or minus 2.5 nanoseconds, which is about 50%, which is a much larger tolerance than it was previous. Some previous CDNs couldn't meet the tighter tolerance of the old standard. With our EMC partner product line, we didn't have any problem with the old standard, but of course, if we met the old standard, we now meet the new standard as well. Duration, the tolerance is about the same as the old standard, just the rise time tolerance has been extended. It's a slightly updated diagram for the new standard, but basically the same. And here's a picture of the setup testing the CDN output. So these are direct outputs through an adapter, the 50 ohm load and voltage divider, and of course the ground. And here's also the EUT output. Both these are basically connected to the same spot inside, so you can use either connection to do your verification. And here's the calibration adapters depending on the CDN, single phase or 3-phase. The capacitive coupling clamp has a new requirement for measurement of the output of the clamp, which there was nothing before. It uses a transducer plate, and that's the plate that's pictured up here. It goes inside the clamp, and it has a 50 ohm termination. Here's a picture of a setup. So you have the 50 ohm or the passive coupling clamp with the transducer plate inside and the 50 ohm termination. So it's calibrated using a generator that's compliant, of course. The calibration is performed with the generator output at 2 kV, and the peak voltage waveform is measured and recorded. So the waveform is basically the same that would be out of the generator. The only difference is the peak voltage is a little lower through the transducer plate. Again, you have 2 kV output with a 50 ohm load would be 1 kV, but we're at 900 volt peak voltage out of the transducer plate. So the advantage of this is obviously you're testing the complete chain, the generator, cable, and clamp, whereas before the clamp was never checked. I've actually heard stories of people having bad clamps where a broken wire or something like that wasn't discovered until, who knows when the broken cable happened. It's the same waveform that's specified at the generator output, so you're just reproducing the same waveform. It's the same 50 ohm termination as used for the generator, so you're reusing the same termination. And the design of the coupling clamp can now differ. So you have a calibration. As long as you meet that calibration, the clamp can be of a different design. Test setup was changed for equipment with elevated cable entries. The old standard had a requirement that the generator and coupling clamp be raised on a ground plane up above the EUT where the cables are coming out. Obviously, you're picking up a 100-pound generator and a clamp on a ground plane and raising it above your head. It wasn't a safe test environment. I don't think too many test labs actually did that kind of setup. So now it's more of a realistic setup that can be done in a lab. EFT coupling into mains greater than 100 amps. So at 100 amps and below, CDN's required. If you're going up to greater than 100 amps, you have an alternative method that you can use. There are CDNs available that do go up to 200 amps for EFT that can meet the requirements, but you do have other options. And basically, put a foil wrap, tape wrapped around the cable that you're testing, and you connect it with a 100 picofarad capacitor to that and direct output of the generator to that to perform the test. Here's some measurement uncertainty tables for calculating that. I'm just going to go over this pretty quickly. It's there for reference. Earlier this year, 61004-5 was introduced, and it's already accepted by SoundLec. So the basic reasons for the maintenance, the waveform definition, reduce it down to one definition before there's two. Calibration of the CDN and generator is with an 18 microfarad capacitor. Define a new CDN for high-speed communication, including calibration. Define a new CDN for the power lines for up to 200 amps per phase. Move the 10700 pulse to the annex and coordinate that with the ITU standard to use that pulse quite regularly. And of course, adding measurement uncertainty. So there's a clear definition of the pulse now. Before, you were allowed to reference IEC 6060 and IEC 6004-69, or either or, I guess, as your pulse definition, but now it's clearly defined in 4-5 and what the requirements are. There is a new requirement for actually calibrating the CDN, whereas before it was kind of not a requirement, even though many manufacturers, of course, calibrated their CDNs to meet a certain requirement, but there was no defined requirement. So from line to line, you have certain parameters, and line to ground. So the characteristics of the generator shall be measured through an external capacitor of 18 microfarad in series with the output both under open circuit and short circuit conditions at the same set voltage. And if the generator has an 18 microfarad capacitor implemented in the generator, no 18 microfarad capacitor is required for calibration. So there are some generators out in the market that implement the 18 microfarad inside, which was the intention of the standard, but it wasn't dictated that it had to be there. Or some manufacturers do not have it. If they do not have it, they have to add that externally to calibrate their CDN. All of our EMC partners, CDNs and generators all have the 18 microfarad capacitor implemented in the generator. So there's no change. We meet all these requirements before the change, and now after the change, of course, we still meet the requirements. If the 18 microfarad capacitor was not implemented in the generator, it could have a drastic effect on the generator and CDN not meeting the new standard. So here's a matrix on how to select the coupling method. There's new requirements for the 200 amp three-phase CDNs, and of course there's a requirement, a new specification for 1 gigabit coupling for Ethernet. So for coupling for different CDNs up to 200 amps, there's different requirements on calibration. So as you get up to this, you can see up to 200 amps, that your tolerances for minus does change a lot, and the same thing for your current ratings as well. And that's because as you get larger in CDNs, you have a lot more inductance, a lot more going on, that it makes it next to impossible to meet the same requirements for a 16 amp CDN as you do for a 200 amp CDN. The other thing too is if you have a 200 amp CDN and are testing an EUT at 32 amps, you still need to meet the requirements for the 200 amp level. Here's some pictures of some high current CDNs. A 100 amp CDN on the left, and on the right here is a 200 amp CDN that can also handle 690 volts AC. So this slide, I'm not going to read the whole thing, but the gist of this slide is that for I/O line testing, you have a choice between, capacitively coupling the surge or using gas discharge tubes. And gas discharge tubes have a lot of advantages and can do the test a little bit better. Here's a diagram out of standard for a unsymmetrical I/O line setup in CDN, and the parameters for calibrating that CDN. So in the past there was no parameters for calibrating the CDN. This has been added, which is could change any CDNs that you have. And of course they have different requirements for the capacitor coupled or gas discharge tube coupled. Setup requirements now require that the AE side of the CDN be shorted to ground. So this kind of includes the decoupling circuit as well in the measurement, whereas before it was always left open. So this does have an effect on a lot of CDNs, where since there was no requirement on decoupling before, this puts a really a clearer cut requirement on that, which may affect some of the CDNs out there. So our solution for CDNs, we have a CDN UTP-8, which was redesigned for the edition 3, again because of the decoupling issue. And we can, with a CDN, we can do unsymmetrical lines as well as symmetrical. So we can meet the requirements of the diagram. For symmetrical lines, the diagram is slightly changed, whereas you have a lot more, try to have a all matched network or injection onto each line so that everything's balanced and it stays the same. And for testing high speed, that becomes very, very important. You have 1 gigabit Ethernet, but also you have much faster Ethernet that's available now. You have 10 gigabit and 40. 10 gigabit has a maximum cable length of 15 meters, and the 40 has a maximum cable length of 7 meters. So per the standard, 10 meter I/O lines are what is what is tested for surge testing. So if you have longer than 10 meters, so obviously the 40 gigabit would not be tested for surge, whereas a 10 gigabit might be tested. But making a 10 gigabit CDN would be very problematic to be able to handle that much data transfer through the CDN and still operate. But the 10 gigabit can be tested at a 1 gigabit speed and still be compliant. A new CDN has been introduced for symmetrical lines for high speed. So again, this keeps everything balanced. It should work much better for high speed lines. And this is in addition to the other diagram shown earlier. The residual voltage. Residual voltage is voltage that's measured on the backside and AE side of the CDN. So say this green pulse here is the pulse out of the CDN towards the EUT, and the red and black are the residual energy that is seen on the AE side. So the black will be seen by a gas discharge tube, and the red would be for residual voltage for a linear circuit, more like a capacitive loaded circuit. The as you can see with the gas discharge tube, you have a very short amount of energy until that discharge or gas discharge tube activates, and then there's nothing. Whereas the red curve kind of over time adds some energy during the duration of the pulse. So you do have a little more higher voltage output with the gas discharge tube, but you have a lot, but it's not very much energy at all. And here's the calibration values for the symmetrical lines. Again, the same thing here is that all the lines are short of ground, which has the decoupling part of the CDN in the circuit. So our solution here, we use the original symmetrical line diagram out of the standard. The new diagram, with this this setup, we're able to meet 1 gigabit Ethernet speeds and our UTP-8 CDN. So we don't need to design a new CDN with a new diagram. The 10700 pulse was moved to the Annex A. And here, I guess the big change here again is the CDN requirement and the calibration of that CDN. Again, with all lines coupled or shorted to ground, and the parameters for that CDN. And our CDN UTP-8 can all couple and measure all these, or couple and meet all the requirements of this 10700 pulse as well. Measurement uncertainty. I'm not going to go too much into this, but one thing that's always important to point out is that when measurement uncertainty is calculated and figured out for your lab or testing, is that the tolerance are not used to reduce any kind of measurement value or tolerances on the actual measurement done in the your setup. It's a measurement uncertainty is a number. It's kind of used to judge the quality of the lab or the setup. It's a mathematical formula for the surge pulse. And some guidance is added also if testing above 200 amps. So if you're creating a CDN for above 200 amps, the inductance would be reduced for decoupling. The 4-19, so this is a new standard to go through why it was created, the actual problems that were seen, disturbance sources, and what's influenced the standard gaps in this range, why a new standard was needed, not just a rehash of another old standard. And of course, we'll go through the new standard. Obviously, energy is increasing constantly every year. It goes up 25%. It's more electrical goods, more computers. You know, it's nonstop. The way to solve this, obviously, new energy sources, solar, wind, geothermal. Of course, the use of existing energy sources, saving energy, variable speed drives, regenerated braking, switch mode power supplies. So this is a variable speed drive which uses pulse technology, which has enormous savings of energy, but it produces a lot of high frequency components to the grid. It's trying to filter it out, but obviously some of this noise still gets through. The same thing in inverters. Inverters will produce a very a low frequency or high frequency component onto the power grid. So the sources of this phenomenon between 2 kilohertz and 150 kilohertz. Lighting equipment, inverters, power supplies, circuit breakers, and of course some household equipment can also produce this, like induction cooking. And the victims of this: lighting, control circuits, heating control, remote control, magnetic card readers, traffic control systems, solid-state electric meters, and this is the big issue right now, is electric meters. And the reason for that is wrong metering values. So if you have a new meter on your home, you don't want to be paying too much, and the electric company doesn't want to be paying too little. So obviously the correct value is important, and this was actually seen in Germany, where they implemented new smart meters, had a couple million installed, and found out that the meters were reading incorrectly. Malfunction of control is possible, and time signal systems could be getting the wrong signals. Magnetic card readers can malfunction, temporary loss of function. IT equipment, again, malfunction of modems and routers, and loss of communication between different communication systems. There was a missing section in the IEC standards. There was really no coverage from 2 kilohertz to 150 kilohertz. Below that, 4-13 was covering it, and above that, 4-6 was covering above 150 kilohertz. But in that range, there really was no standard for differential mode testing. A few years ago, 4-16 was created for common mode testing that overlaps that range, but not differential mode. So that was the reason for the creation of 4-19. Of course, when you're creating a standard, you have probability distribution curves. You have what the real world is emitting, and what you're testing to, and what you want your immunity to be on that equipment. And of course, you want a safety margin between the two. In the basic standard, you have a definition and description of one phenomenon that's supposed to be very limited. Test and measurement of the method specification. You have test instrumentations listed, basic test setup, and a range of test levels, and of course measurement uncertainty. The basic standard are modules for generic and product standards. So that's kind of important. The generic and product standards would define what's not included. So obviously the limits would be defined in product standards. Performance criteria for product-specific test arguments, and of course test sequence would all be done in the product standards. So calibration of the generator according to the calibration procedures based on the standards. So the idea is have a test that's reproducible and can be done in a decent amount of time. And then once you calibrate it, you hook up your EUT, and whatever happens, what happens. The EUT is kind of a black box. So 4-19 was created earlier this year or finalized. This is a basic test equipment. You have your generator going through your CDN and your EUT. So you calibrate at your generator, you calibrate at your CDN. The test standard is for differential mode only. If you need to do common mode testing, the 4-16 should be referenced. Sweep tests is, there's two different tests. There's actually a voltage test and a current test. And then there's two different types of modulation. There's a common continuous wave pulse, which is a swept kind of test, and there's a more of a block rectangular modulation, which is more of a pulse modulation, short duration pulse modulation. So power line communication equipment would most likely just get voltage testing, whereas a measurement or equipment that actually does measurement of current would be tested with current as well. So electricity measure. These are 4 different test levels. CW tests, again, is a long duration. During this duration, the frequency is swept. And then the second modulation is short pulses, and each pulse would have a different frequency. It's verified into an open with a differential probe, and then shunted with a shunt for current measurement for your calibration. And of course, your CDN also needs to meet a certain criteria. So the insertion loss of your CDN is measured with a network analyzer. Here's a setup for voltage test. Generator through the CDN, and you have your equipment. And here's our setup for that. Again, it's a generator feeding the power for the EUT and the CDN. Now for the current test, when you're doing electricity meters, you have both voltage and current at the same time. So here you have a lot more complex setup. Right now we're the only solution on the market for this type of test. You have your energy meter, which has both voltage and current measurements, and it has to be tested simultaneously. So that's it about the 4-19 new standard. We're going to go into MIL standard 461. And quickly go over the new requirements for that for power and I/O line testing. The current standard is 461F, of course, which supersedes the old standards, but as everyone knows with MIL standard, that the old standards still come into play when you're testing equipment for old platforms. They have a CS106, CS115, and CS116. So these are the transient tests out of the F version. CS115 is unique to 461. No other standard really has this kind of a test. This excites a natural resonance and EUT cabling. So kind of a switching test produced on the cable. You have a very fast pulse, less than a 2 nanosecond rise, less than a 2 nanosecond fall, 30 nanosecond duration. Here's a measurement of one of our generators' output to show the same thing. This is the output out of the clamp into the fixture. CS116 was previously CS10, 11, 12, and 13. It's an EMP excitation of the cable bundles. And of course the waveform is defined at the system interface. And it has fixed frequencies. So you have 10 kilohertz, 100 kilohertz, 1 meg, 10, 30, and 100 megahertz. And it's the dampened oscillatory type wave. Cosine is also allowed. If you're using a cosine injection, you use the first full sine as your first peak, and then your damp is figured out for that one. And here's a test level for that. And here's our setup for those 3 tests. 461G, it's important to state that this is a work still in progress. So all information here is subject to change before release. Information purposes only. Anything can change, anything can happen. These tests can go away or be completely changed before it's released. But what may come in the update is that they're going to add lightning tests. These are kind of based on the DO 160, section 22. and ESD tests, and this is based off of IEC 61004-2. There's also text being added to clarify the use of FFT-based receivers, and FFT-based receivers can be used now. It's just they have an enormous time-saving capability and can still produce the same accurate measurements. You can dwell and get much more information off the EUT with an FFT-based receiver and still reduce your test time by many, many, many times. But they're going to add some clarification on its use. So G, as you can see, you have CS117 listed and CS106 listed. This is his new test. One thing that's missing is CS106, which seems to be removed. Last I heard, it's still there's the Navy required 106 to be added to F, but I think that it's been pulled back again. We'll go over CS117. It's lightning-induced transient and cable power bundles. It's applicable for Army, Navy, Air Force, of course for aircraft, and space vehicle right now is limited. Again, this is all provincial. It requires most of the waveforms for DL160, Section 22. You have multiple stroke, multiple burst. It's specific test levels. So what's not included is single stroke and pin injection. So here's a draft table of the test levels. The test levels relate to DL160. Of course, it's levels 3 and 4. Relatively, they're a little different though. But and you have waveforms 1, 3, 5A, and in multiple bursts you have waveform 3 and waveform 6. So waveform 1 and 5A are the slower waveforms, which will be done with our MIG 0600 MS generator. And then waveforms 3, which have 2 frequency components in there, and then multiple bursts, waveform 3 and 6 will be done with our MIG 07 MB generator. And if you're currently testing to the DO160 requirements and have level 4 capability, you will be able to meet the mil standard requirements. There hasn't been any changes to test equipment or anything like that. For the ESD testing, the test requirements are pulled out of IEC 61004-2. At one time, I think I heard levels up to 25 kV. Latest I heard it might be just up to 15 kV. It all depends on, I guess, what the final release is. It's a standard 150 picofarad, 330 ohm circuit out of 61004-2. This is also the same circuit that's used in DO160. So if you can do that as well as for ESD, you can do it for mil standard now. One kind of special requirement in mil standard is that they have a pre-test verification requirement. So we have a nice little device for verifying the voltage out of the ESD gun. So you just plug the ESD gun into a voltage divider. It's a 2000 to 1 voltage divider, and you can measure the voltage of the charging of the circuit with a DVM or a scope. And of course, verification of the pulse itself is done with a target that's called out in 61004-2. One thing that mil standard is only asking for a 1 gigahertz scope bandwidth for use with the target. The IEC requirement is 2 gigahertz or greater. We suggest a 4 gigahertz or greater, and that's because the target itself is actually designed and built for 4 gigahertz, and there's a lot of frequency content in the pulse that you'd be missing without the added bandwidth. But of course, if that's what you have, but if you're purchasing something new, it'd be nice to get what you need. And of course, as 461G moves forward, final draft is planned to be distributed early 2015 to go out for industry and public comment. And the plan is to have a final release, after all that is answered in late 2015. And again, all that could change what I've just discussed 100%. Anything can happen before it's released. Thank you very much. So that's it.
Jason, thank you so much. That was very informative. Before we open our Q&A, I would like to ask you to submit any questions that you'd like Jason to answer. We had kind of a quiet bunch. We are getting some nice comments. It was very well received, Jason. So I will put out this last call for final questions. Jason is more than happy to answer any specifics. While we wait for those questions to come in, I will remind you that a recording of the webinar will be available on the website next week, and all of those attending will get a link sent directly to you. It looks like we'll give you a few more minutes in case anyone wants to send anything in for Jason. Today is the last day of our three-day event, so don't forget to check the website. We have a full day of webinars and roundtables. You can find the schedule at www.emclive2014.com. At this time, I would ask if you think of a question, please feel free to email us at info@emclive2014.com, and we will forward it on to Jason, who has offered to answer any questions that may come in, and we will post the content on our website. Well, Jason, at this time, I'd like to thank you for your time and expertise, and to all of you for attending. Oh, wait, we have one. We do have time to take a question that just came in. Jason, our attendee asked, there have been many ways to calibrate 61000-4-4 CDN over the years. What do you prefer?
I guess trying to figure out, there are many different ways. Well, I mean, the way to calibrate for 4-4, the CDN, the preferred way, you know, if you're doing common mode, everything's coupled at the same time, and then you would go through each line individually and verify that each line meets the requirements. I guess the previous one of the versions, I just shorted all the lines together. The downfall of that is if one line was broken inside the generator, you would never see it. Of course, I think the newest version of the standard takes care and kind of covers everything that could possibly have been missed in the past. So I think that's the best way of calibrating the CDN now.
Okay. Another question has come in. Is there an expanded version of this presentation? Oh, perhaps in future conferences. We'll go ahead and send a direct response on that. We will have an archive of this actual webinar on our website, and a downloadable PDFs will be available for all that attended. Okay, Jason, thanks again for your expertise.
Thank you.